Alright, so today we're going to talk about commutation relationships and how they play a fundamental role in quantum mechanics. So, the commutator of two different operators is going to be defined in this way. So, it's also going to be an operator too. The commutator itself is an operator, just like the operators it's defined with, A and B. And we define it as the operator A. Well, okay. You have AB minus BA. And this ideally is going to act on some wave function. Now, the operators that we always use are going to be linear. So if we decompose this definition is really saying this. Well, not decomposing the definition, but if we acted on it with a concrete function, then this is what we get, assuming the operators are linear. So if the two operators commute, if acting on B then acting with A is the same thing as acting with A then acting with B, then the commutator should be equal to 0. So the commutator is going to be a concrete measurement of, can I flip these operations around? And that's going to turn out to be a very important thing. Because, just for a concrete example, the position and momentum operator, do those commute? Well, if we just apply our definition of the commutator, and we write xp minus px operating on psi, well, like I said, we're only going to be interested in linear operators, so we can break this up into two different parts, where we have xp psi minus px psi. And if we look at the left side for a minute, so we have x hat, p hat, acting on psi, we should read this as the following. We should act with p first, then act with x. Just like function composition with regular functions. In fact, that's what these operators really are. So, if I act on psi with p, well, I'm not operating with x hat yet, then I would get h bar over I times the partial derivative of psi with respect to x. And then, if I act with x on that wave function, well, I just get h bar over I times x partial psi over partial x. Now, if I look at the other side, so if I look at acting with p first, then acting with x first, then acting with p, I'm going to run into some problems. Well, I shouldn't say some problems, but it's not going to look like what we just got when we acted with p first, then acting with x. Because if I act with x first, then I'm going to be acting with p on x times psi. As you can probably imagine, this is going to cause some problems, because now I'm going to be taking a partial derivative with x times the wave function. So when I do that, I get h bar over I x partial psi over partial x. So this is what we got above, but then we're also going to get an extra term. We're going to get a plus h bar over I times psi. So if I take this from up here and subtract this, so this term up here, and I subtract this and subtract this, then in my commutator what I have left is just h bar over I times psi. And, whoops, my bad, I have a minus h bar over I right here, because these go away together. But if I have a I on the bottom, I can put it on top for convenience at the cost of a minus sign. So that minus sign goes away. So it turns out that the commutator of x and p is not 0, so it does not commute. Acting with p then with x is not the same thing as acting with x then with p. So we would say that the commutator of x and p is equal to I h bar I hat, where I'm just saying I hat is the identity operator. It's the operator that you toss at a function and it gives you the same exact thing back. So commutators like this, simple ones like this, where it's just a constant, have a simple physical meaning. But to understand why that must be the case, we need to figure out in what case is the commutator actually 0. So when can I just flip the order of the operations? And the answer to that turns out to be whenever the function you're acting on these operators with is an eigenfunction of both the operators a and b, per se. So if it's an eigenfunction of both, what we're saying is if we had some function psi that was an eigenfunction of a and b, well, when I act on psi with a, I should get just some constant times psi. That's what it means to be an eigenfunction. And for the second one, if I act on it with b, I should just get some constant times psi. So if I look at the commutator of this now, so I have my AB minus BA acting on psi, and we're always going to be worried about linear operators, so we can decompose that into the AB acting on psi minus the BA acting on psi. So what's B hat acting on psi? Well, that's going to be B times psi. And then if I act with that with A hat, then I'm going to get A times B times psi. And then with the other one, if I act with A hat first, then I just get B hat acting on A psi. So I'll just write that over here. So B hat acting on A psi, well, if I act on B hat with this, I should get B A psi. And these things, well, since these things are actual numbers, then when I just subtract the two, it's going to be 0. So it turns out the commutator is going to be 0 whenever the function that you're dealing with is an eigenfunction of both the operators. So how does that relate to position and momenta? Because that seems pretty unrelated. Well, if we wanted to try to put our system, in a state of definite position and momenta, then what that would mean is, remember, we can always represent our state as a superposition of eigenfunctions of our operators x, p, or E, those Hermitian operators. So if I try to put it in a state of definite position and momenta, it would need to be an eigenfunction of both. So that's going to cause problems though, because if my commutator, regardless of the function psi I plug in, because the commutator in the end isn't dependent on psi, it's just equal to IH bar. Well, that means I can't do that, because if I put it in a state of definite position, then it can't also be an eigenfunction of P, because, well, my commutator can't be 0, it's IH bar. So this commutation relation is very important, so I recommend that you memorize it. The commutator of x and p is IH bar, and it's what forms the basis of the uncertainty principle. So commutation relations are very important. So one more trick that we can do with operators, and then we'll finally be able to apply all this stuff, is to commute an operator through. So, as we just discussed, operators in general may not be commutative. So if I've got a situation where I've got AB acting on psi, and then let's say for one reason or another, I wanted to act with A first. Like perhaps I know psi is an eigenfunction of A. And so it would be useful if I could do this. But if it's not a commutative operator, I can't. But it turns out there's a trick. So if I've got AB acting on psi, we can do a cute little trick. So what we're going to do is add 0. But probably a little suspicious now. So what this 0 actually is BA plus BA. So I haven't changed the problem. I've only added 0. And we know this is 0 because if we assume these are linear operators, then we'll actually be able to factor it and show that it actually is equal to 0. So how does this help me? Well, this right here, AB minus BA, that's the commutator of A and B. So, wait, whoops, that's supposed to be a square bracket. And then I've got BA. So now I can act on psi with A first, like I said, at the cost of the commutator. So this trick is particularly useful whenever the commutator has a nice simple form. Like the commutator of x and p, well, that was just equal to IH bar. So as we'll see in future videos, that's going to come up. We can actually commute operators through and lead to some really nice results. So I hope you enjoyed this video. Let me know in the comments if you did. See you in the next video.